Hello and welcome to Cut Saturn Heated Square Cavity tutorial. This video will give you a preview of how to set and to compute a CFD case including Boussinesq buoyancy approximation. I will show you how to set this CFD computation and give you previews of the results with ParaView software. In order to optimize the video duration, I will focus on the CFD settings and the post-processing results. Please refer to the PDF tutorial if you need details on how to create and generate geometry and the mesh. The latest is similar to the Sqaure Cavity tutorial. In this case, we want to perform a computation referring to the classic natural convection benchmark cases of Duval, Davis, and co-workers. A viscous fluid is contained in a two-dimensional square box. All the walls of the cavity are fixed. The horizontal walls are isolated and adiabatic, and the vertical walls are kept at constant temperature. The left vertical wall is a hot wall, while the right vertical wall is a cold wall. The acceleration of gravity points downward in the vertical y-axis direction, and we hope to find and expect natural convection results. Let's now set the case. Setting this case is pretty quick. First of all, and as usual, you need to create the case and its subfolders. As you can see on the right, I created Heated Square Cavity folder, included case 1, mesh folder, and post. Make sure the mesh file is well pasted into mesh folder and all sources file pasted into src subfolder. Once this is done, move to the graphic user interface of Cut Saturn of this case, then proceed to the standard procedure. First of all, save your XML document. Then move to Mesh tab. Make sure the mesh file is well selected and the standard computation option is also selected. Under the boundary zone, make sure these criteria are also well set. You will have more details in the PDF tutorial if you need to set this in a different way. Once this is done, you can save your XML document, then move to Calculation Features. Select Standard Hulayan Single Phase. Then, no need to activate Turbulence Model, but you need to activate a Thermal Model and select Temperature in Kelvin. You also need to add -1G following the y-axis. You don't need to add species transport neither. Once this is done, you can save your XML document and move to Volume Condition. Under Volume Conditions tab, make sure Physical Properties and Initialization are both ticked. You can select all cells, then initiate the thermal values up to 293.15 Kelvin. Regarding velocity, all components could be set to 0. So now you're done with initialization and you can move to Physical Properties. Make sure all of these values are also set on your side and the user load is also set as follows with this mathematical expression density equal rho. Once this is done, you can save your XML document, move to Boundary Conditions, make sure all labels are also well set and the nature of walls also selected. You don't need to change any of these values. Regarding symmetry, that's normal. Adiabatic, you don't need to add the values here. Regarding hot wall, you can set the hot wall temperature up to 303.15 Kelvin and the cold wall down to 293.15 Kelvin. That's 20 degrees difference. So once this is done, you can save your XML document, move to Time Settings, select Time Varying under Time Step option with a simplex algorithm, increase CFM number up to 8, then set the number of time steps up to 450 steps. You don't need to set start restart option, and you will be done with time settings. Under numerical parameters and equation parameters, and under clipping tab, set the minimal value of temperature down to 293.15 Kelvin and the maximal value 304. That will reduce and to prevent spurious from poisoning calculation in this case. So once this is done, you can also move to post-processing under surface solution control. Then you can just unselect Y plus and stress. You just need to select dimensionless thermal flow, boundary temperature and thermal flow. That will be enough for this case. Once this is done, you can save your document, then you can proceed to run computation, then run calculation. Let's now move to the post-processing phase of this computation. As soon as the computation is done, you can load the results into ParaView. Make sure to load results fluid domain and select the filter cell to data to point data 1. You could also create a slice to have a clearer view of what's going into the cavity. So once this is done, you can plot the temperature into the cavity and you should have this kind of results. This is what we expected, a kind of convection. On the right we have a cold wall, and on the left we have a hot wall, and you have this kind of convection, natural convection appearing. What could be better is to create isolines. In order to do that, you need to select contour, and here you have a contour of isolines. We will make it clearer. And here you have the domain around the isolines. We could also do this with velocity. In order to have a velocity view, we need to create streamlines. This option is located here. It's not called streamlines, but stream tracers. And you need first to create a slice, then create stream tracer based on this slice. And as you can see, you have the streamlines appearing and the range of velocity. So velocity values are quite small, but also we could also see the natural convection appearing here. This concludes this video tutorial. I really hope you enjoyed watching this video. I highly recommend you to keep tracking Sqaure updates by checking on our channel or social media pages to get the latest news. Thank you for watching.